Alright, so in this video lesson we are going to learn about factoring by GCF, and precisely factoring by finding the GCF and factoring by grouping. So this can be understood as the beginning lesson in all of the techniques, all of the methods about factoring an algebraic expression like that. And more specifically, we are going to drive our attention into the factoring, applying these methods into all of those polynomial expressions. Okay, and so let's begin our lesson here with the very primary skill that everything else built on top of that is the method, is the concept of how we can find GCF. So now let's begin our stepping stone right here. All right, so we begin our lesson here, and that's how I teach that. Anytime leading my students into being able to factor a polynomial expression, we definitely have to, must know how to find the GCF of some two, the expressions. Okay, so let's begin with something like this, and I gotta be clear. This method right here, some viewers, some students learning in this lesson right here might have seen this, might have learned this from prior to this course. Take all of your experience into that, and any experience you have had into this, that counts a lot. So what I show here is the most universal method right here, but if you find a way to do things more efficiently, effectively, and even faster, go with that. But the goal is to find the GCF. So first of all, GCF here is short for the greatest common factor. All right, so that's what GCF is for. But see, it's lengthy for a name, lengthy enough that nobody is calling that with that long name, greatest common factor. For short, we call that finding the GCF. But let's really get to it. So let's say I'm going to come up with some two numbers, and let's begin with a level that everybody knows. So we're having some two numbers, 18 and 24. So these are just some two numbers right here. And from your previous understanding, from your previous background that you have already had, these are two composite numbers right here. They're definitely not primes. Okay, but the method we're about to learn also applies to prime numbers as well. So 18 and 24, we got two numbers. Our goal now is just think about it like this. And before I dive into the actual technique, just think about it like this. See, let's say 2 is a factor of 18, and 2 is also a factor of 24. Okay, think about it for a moment. The number I list down right here, see, I see in 18, there's a factor of 2 that goes into 18. That's a different way of saying it. I see there's a factor of 2 that goes into 24. Okay, so between these two numbers, 2 is a common factor. Okay, so now I'm seeing that 2 is a common factor, and that's the idea that begins the idea of common factor. Okay, any number, a lot of numbers that we have here have common factors. But so now that raises a question. So wait a minute. So 2. Right now, 2 is a common factor. So what about 3? Somebody else can think, and at some other instance, you can think, hey, wait a minute, 3 is also another common factor. Okay, and so 3 is a factor in 18 and also a factor in 24. So now all of a sudden I realize, hey, wait a minute, 2 and 3, they're both common factors. So now I have to modify my wording. So I realize there are more than one common factors. And so that comes to the idea, hey, and among the common factors we have already found here, 3 is greater than the other one. And that's where it leads to the understanding, hey, what about, let's learn how to find the greatest common factor. So I did that brief introduction for you to realize between any two numbers, there will always be some common factors. Okay, and then among all of the possible common factors, we're looking for the greatest common factor, and once we have found it, the GCF, once we have found it, it will be the unique common factor, which is the greatest common factor, and then there can only be one unique common factor, the greatest common factor. Okay, so in that way, so now getting along to that. So now our goal is clearly to find the greatest common factor. So let me switch over to the other board of mine. And so, in order to find the common factor, the greatest common factor, I need to bring in a skill that you should have learned in a course prior to this. So, and as I mentioned it, you will recognize. Let's say 18 right here. Using the method to find prime factors. So prime factors is a concept that you should have seen that you should have learned in your previous course. So finding the prime factors of a number, that's the skill you should have learned already prior to this course. So 18 right here, in terms of prime factors, 18 has 2 as a prime factor times 3 squared. So I have just now expressed 18 here as a product of 2 prime factors, 2 and 3, but 3 here is a square. Well, think about it. 18 we know by heart is 2 times 9, but 9 is a 3 square. So writing things, and that's why, like I said, the being able to find the prime factors is one skill that you should have learned prior to entering this course right here. So 18 here is a product of 2 as a prime factor and 3 as a prime factor, but 3 here, there are 2 factors, there are 2 prime factors, there are 2 repeated factors, 3. That's why it's a square here. So that's just a little bit of a repeat of your past understanding. And so in that way, using and the method that we find prime factors, for you to know, again, you might have learned this term already, but finding the prime factors from a number, we call it it's a prime factorization. Okay, so prime factorization refers to a process where you re-express a number as a product of prime factors. Okay, and of course exponents are included. All right, so in that way, going with prime factorization, I am going to find the prime factors of my other number. So 24, expressing 24 as a product of prime factors, I'm looking at 2 squared times 3. All right, so again, using prime factorization, or finding all the prime factors of 18, we express 18 as a product of 2 and 3 squared. We express 24 as a product of 2 squared and 3 squared, and 3. And so these are all the prime factors. So this is how we're looking for the common factor, the greatest common factor. So as a method that I commonly use, as a method that I use on a daily basis, see, 2 and 2, 2 and 3 and 3, these are all common. See, it's common. The 2 are the common. Now, for now, before worrying about the powers, the exponents here, at least I see the 2 is a common factor, a common prime factor that's recognized between the 2 numbers here. So I write down that common prime factor first. Aside from that prime factor 2, I recognize another prime factor 3. And again, let's just recognize them without the exponents. So I have a 3 right here. Okay, so I put it in as a product. Okay, and now each of these common prime factors has various different powers. Say, for example, the common factor, the prime factor 2 right here, it has power 1, exponent 1 in 18, but exponent 2 in 24. We want to choose the least. So the least among the numbers right here, this common factor 2 has the least power in being 1. The least power of this prime factor 2 is 1. So we bring that in as a 2 to the first power. So remember, my word here is after picking the common prime factor, we pick the one with the least exponent. Okay, so among the different ones right here, 2 to the first power, 2 to the first power is being included in our GCF. Okay, so in that exact same philosophy, in that exact same the guideline right there, I am going to go with 3 right here, and I pick the least one, the least exponent for this prime factor is a 1. And so now that's how we complete. And so multiplying out these 2 prime factors with their corresponding powers that we chose, then 2 to the first power is a 2, 3 to the first power is a 3, 2 times 3 equals 6. Okay, and so now, ladies and gentlemen, the GCF, Okay, the final GCF. So in the end, GCF here, something we're looking for is a final number. So GCF that we found for the two numbers here equals 6, and that's how we have done it. And so that introduces the methods of how we can find the greatest common factor. Okay, so in that way, let's look at some examples. And now I'm starting with example 1. All right, so in this problem, I would like to find the GCF of 48, 80. And so the example here strengthens the method that I have shown previously, and also sets anyone learning from the lesson here into a certain routine of how we can carry out the steps. Okay, so in this example 1, again, very similar to how I have done in the demonstration work earlier. So I have two numbers, 48 and 80. Okay, and so now the first step looks like, according to the method I've shown, right, the first step into finding the GCF here, I have to find the prime factors and express 48 as a product of the prime factors. So 48 here is a 2 to the 4th times 3. 48 can be expressed as a product of 2 to the 4th times 3. So 2 is a prime factor and 3 is another prime factor. Okay, and again, how I can find this, that requires some skill that you should have learned back in your in your previous course. All right. Now 80. Okay. 2 to the 4th times 5. 80, after doing prime factorization, or after finding the prime factors, 80 can be expressed as a product of 2 to the 4th and times 5. Okay, and so I have found all the prime factors in 48 and 80. And so now let's recognize the common prime factor. So the only common prime factor is a 2. Okay, is a 2. And so in that way, once again, the way how I do it, the GCF here can be found by simply choosing the common prime. The common prime factor that we recognize is a 2. And it has different various powers, but here the least one is of course a 4, and it happens to be the same in both cases right here. In both cases right here. So we got 2 to the 4th. 3 is a prime factor, but it's not common. 5 is another prime factor, but it's only existing in 80, not common. And so we don't include these. All right, so in the end, 2 to the 4th power is 2 times 2 times 2 times 2. 4 factors of 2 multiplied together. So now in the end, our final GCF is a 16. All right. So we have found the GCF for 48 and 80. And so for a problem like this, then it's just a very elementary problem. So it's just pretty straightforward with the instruction that says, hey, here you go, two numbers, and we find a GCF right here. So this is just some alternative understanding, just some optional understanding. If you like this, you learn, you take it. If you don't, that's okay. You can ignore it. But you may start seeing some more in some more advanced courses, which are waiting for you. Then people may express things like this: GCF in parentheses right here, 48, 80 equal 16. That's one way of saying, that's one way of making a statement that, hey, the GCF of these two numbers, the GCF of 48 and 80 is 16. That's just some way to communicate the answer. GCF of 48 and 80 is 60. But this is just an optional notation right there, the symbolic statement right there to indicate the answer. But as far as formal work, this is everything we need to do. We need to know. All right. I would like to bring in another example. Let's call that example 2. And we're still doing the exact same instruction as in the earlier example. You get to see the repeated steps for finding the GCF again. but I'm gonna bring in some further experience, okay, to enhance your learning. Okay, so let's find the GCF of how about 4x squared y and 6x y cubed. All right, so the work for finding GCF will now become a little more advanced because the class we're doing here is an algebra class. We're no longer doing basic arithmetic course anymore. So the problem that we have seen in example 1 was a problem for the middle school students can do, elementary students can do, okay? But we're now in a formal college algebra course, okay? So we are well familiar with these are what so-called algebraic expression right here. So what we have here is a term, it's a product of a 4 times some unknown square. So the unknown here we call x, it's the variable, okay? So 4 times x squared times y. So 4 times x squared times y. So this one expression right here is a product of 4 times whatever x squared times whatever y. Okay? And then aside from this expression, we have another algebra expression. 6 times x to the first power times y cubed. All right. So now let's find the GCF. Okay, so the idea again, we're going to learn the technique, the method that we've done in example 1, and we've seen in the illustration, and we've gone through the example 1, and let's apply exactly the same way here. So this expression for x squared, y squared, it's ridiculous that I'm writing this down like this, but in the way how it looks right now, in terms of prime factorization, it's the 4 here as a prime factor is a 2 square, okay, times, and then the x squared, x is a variable, so the only thing different from what we've done in the example 1 and what we've done in more basic arithmetic course is that now x here, it could be a prime, it could be a composite, but in the end, it doesn't matter. We can just leave that. We can treat that purposely. We can treat the x here purposely as a prime factor, even though we're not sure it's a variable. Okay, so it's x squared. So we can purposely see x here as a square. So I am doing prime factorization on this particular term right here, on this particular algebraic expression. And so times, right, as a product, I've been saying it's a product, right? Y to the first power. Right, so I have now just done prime factorization. So what are we learning from here? When you have an algebraic expression like this and finding the prime factorization, all we do is just simply, once again, do the prime factorization on the coefficient. And then for all the variables, they just remain pretty much the same with whatever powers that they come with originally. All right. And now for 6 times x y cubed, here's how I can do the prime factorization for that. 6 here has 2 prime factors, 2 times 3. So the product of 2 and 3 gives me 6 times x to the first power. Like I said, it's a variable now. We treat that purposely as a prime value, a prime number. Okay, so x, no power indicated here, it means it's first power, times, and then in product with y, it's another variable, different from x, but we see that as another prime number, cube. All right, so now this is the list. These are the list of prime factors in each of our expressions here. All right, and so now let's recognize the GCF. So the GCF here, to come up with the GCF, we're just going to once again go through the 2 expressions here of the prime factorizations, and we're going to collect common prime factors. So the first common prime factors I recognize is a 2. All right, so 2, and the common prime factor 2 here appears in both parties with varying powers. So we choose the least power here. It was originally 1, so now I'm going to go with 2 to the first power. All right, so I'm done with the common factor 2. 3 is recognized as a prime factor in this other algebraic expression here, but it's not in the other one. So I won't include 3 in here. Okay, the x is a common factor. All right, so I'm going to put x in, and once again, clearly x as a prime factor shows various powers or exponents. So we choose the least one. So the least power that we include for x is actually the first power. All right. Y is another y is another common factor that we can recognize among the two parties here with various power, and 1 is the least powers among the two. So we put in y to the first power. So in the end, this is how we can express our final GCF right here. So as a next step, really, I'm just rewriting the GCF here is found to be 2xy. See, 2 to the first power is 2. X to the first power, which is simply write it as x. Y to the first power, we simply write it as y. So 2xy is going to be our greatest common factor of these two algebraic expressions. All right. All right, so now we have another problem. And what you have learned up to this point, you've seen the steps twice or even 3 times. And so we're going to apply the exact same steps. I just want to add in more experience and to bring in different cases for you to become better. So again, what I have here is an algebraic expression. So what I have here is a 10x squared in products with a whole x plus y. So now I would like anyone viewing this lesson to see this as a 10 as a coefficient. It multiplies with x squared, and then x squared is multiplied with the entire parentheses expression. So the entire parentheses expression here is exactly 1 factor. I mean, it's easy to see it that way because according to PAMDA's order of operations, right? Anything that's included inside of parentheses, we have to count it as 1 unit. And so since there's products all over here, so it's this entire unit, this entire parentheses expression is multiplied as a factor with the x squared with the 10. So now applying the prime factorization process right here, finding the prime factors of this expression, the best we can do is now the coefficient. Similar to the earlier example, the coefficient here is a 10. Now I can write it as a product of 2 times 5, and that's about all of the prime factors for 10. Just like that, the x squared right here, I'm going to see that simply as a prime x squared. What about the scary looking expression right here? Well, if that's all it is, we have our right to just write it x plus y. That's all it is. I've been emphasizing that. Let's treat it as 1 unit. So I take the whole thing here as 1 unit, 1 variable, 1 big crazy variable. We put it there as a prime value. All right, we're doing the similar thing for 15xy times x plus y. So now finding the prime factors. 15 has prime factors 3 and 5 as a product, 3 times 5. X times x to the first power times y to the first power and times x plus y as 1 unit. I mean, the whole x plus y here is 1 unit. That's what I've been saying. And so now in that case, to find a GCF, once again, we're repeating what we've been doing. Let's look for common factors, common prime factor. 3 and 2, they're not common. The 5 is common. And also, it looks like the least power between the two 5s here, that's power 1. So I'm putting in, it's 5 to the first power. Another common factor I can recognize is the x. And it comes among the two parties, it comes in various powers. We pick the lowest power, we pick the least power. So here it's times x to the first power. Y here is a factor of this bottom one, but y is not a factor of the other one. Now, not that y. Now, that y is included as 1 unit in here, so you only see the x plus y as 1 factor. But the y here doesn't count as a factor in this whole product. All right, and that's what I've been saying, maybe in case it wasn't clear earlier. Now, I hope it clarifies a little better. So this y here as 1 factor is in this expression, but not in the other one. So we cannot include a y in here. But the whole x plus y, and x plus y, that is a common factor, common crazy big factor. We can include it there. And the power here is 1. It really didn't write, but it means power 1. So we put it in x plus 1. So in the end, our final GCF appears to be 5x times x plus y. That's the common factor. That's the GCF, the greatest common factor between these two algebraic expressions. All right, so now we are at really that technique, how we can factor a polynomial expression by finding the GCF. So this particular topic here must be learned completely after you have mastered, hopefully, the skill of how to find GCF of some two numbers and the GCF of some two algebraic expressions. Okay, and so let's dive in right here. Now, allow me to clarify what a polynomial expression is, because we have to have a decent understanding. You may have seen this term already quite often in your previous courses, but in case you're still going a little shaky with the solid understanding of what a polynomial expression is, then here we go. So a polynomial expression is basically, it can have, see, let's say like a 4x squared y, okay, and then there's a plus 3xy plus, and then maybe let me creatively put a minus here, it's 4. Okay, so this is a mathematical, what I see here is a mathematical expression. It indicates an expression, a mathematical expression tells you what you can do, what kind of operations are involved in a computation. So this is a statement that indicate here, hey, there's a computation. You go 4 times whatever the value for x square and multiply with y, and then the computation doesn't stop there, it goes further, and then we add with 3 times x times y, and of course order of operations counts, and then minus 4. So there's order of operations all involved, but in the end, what we have here is a mathematical expression. It indicates some computations going on in this written statement right here, this written symbolic statement. Okay, it tells you clearly what to do with the variables, and then what to do with the numbers all mixed together. Okay, but then what exactly? So we understand what an expression is, but what is a polynomial expression? A polynomial expression. See, poly means multiple. So you can see that here we got adding and subtracting, addition and subtraction. So focus right on those addition and subtraction. It separates out. These are the terms here. And so poly here means around those adding and subtraction signs, and we got multiple terms. Okay? And then each term, now so let's look a little closer into each term. Each term has only coefficient, product, and powers. See, products, coefficients between a product between coefficients and variables and powers, and maybe some divisions. Okay, but that's it. Okay, 3 times x times y, that's one term. A product or a division or a quotient between numbers, okay, variables, okay, or one single number itself can be regarded as a term as well. But then the addition sign and the subtraction sign, it separates the terms here. So when we focus on that, between these, around those are 2 terms. And around that minus sign right here, those are 2 terms. So the entire expression here, we call it, it's a polynomial expression. Okay, and it got 3 terms. And how we can detect the terms here, plus and minus, those separate out the terms. So these signs right here indicate we got a term here, a term there, and a term here. It's a term, it's a term, it's a term. Okay. So each one of those I underlined right there. Any one of those is a term. So those are the terms. Right? So that's what a polynomial expression is. And then so of course, aside from this main video lecture right here, I will have additional video clips for you to get better at recognizing what a polynomial expression is. But allow me to stop here in terms of explaining what a polynomial expression is. And so now we begin the idea of factoring a polynomial expression by finding the GCF. Okay? And so let me bring back some past understanding. Let's say in your previous courses you have learned this special property right here. When you have a 2 multiply or in product, and sometimes I can even skip that. Sometimes I can even skip the multiplication dot sign right there. Let's say a lot of times textbook authors write it like this: 2 in parentheses x plus 7. Okay. What this expression here says is that you have a factor 2 and it's multiplied with a product that it's multiplied as a product with a parentheses expression going x plus 7 inside. So a product between 2 and a sum x plus 7. So you have here is a sum and then 2 times. Okay. And so with this one here, I've been mentioning about your past understanding is from your past learning courses, you have learned that you can multiply the 2 separately with x and the 2 separately with 7. So making it 2 times x and then 2 times 7. So we're producing 2 separate products and we can add those 2 products together. This is what's famously been understood, been introduced as the distributive law right here. The work I've just now done is called the distributive law or the distributive property, okay, for multiplication. And so now algebraically, 2 times x can be rewritten as 2x. And you should be fluent with how we write an algebraic expression like that. And then 2 times 7 is a 14, so plus 14. Okay, so that means using distributive property, that means 2 times with this product, 2 times with this sum right here can be broken down as 2 separate products and added together. And so you can see that 2 times x plus 7 equals 2x plus 14. And the way I made my argument was right here. The distributive property was the leading reasoning that leads to this. So now we can loudly say that these are equal. Okay, but now if you're looking at this final statement a little more closely, 2 in products with the sum x plus 7 is equal with 2x plus 14. You can think of that as in the other way around. It also means you can argue that, hey, starting with an algebraic expression 2x plus 14, what I see here is a polynomial expression. Okay, that addition sign separates 2 terms, so that's why it's polynomial. The first term here has only products or division. Now division is not directly involved here, but see, products between coefficients and powers, variable with power, and then or a one lone number. It's a polynomial. So in other words, what I'm seeing here is 2x plus 14 as a polynomial expression. What I'm seeing here currently is a polynomial expression. So this polynomial expression can be argued that it's equal exactly with 2 in products with a sum x plus 7. This is a product between some 2 factors. So 2 is a factor, and then x plus 7 is another factor. All right. But the point I would like you to see now is that a lot of time, starting with a polynomial expression, we can bring that polynomial expression, make that equal to a factor product. So this one right here, 2 times x plus 7 is called the factor form, okay? Or sometimes the factor product, okay, of 2x plus 14. All right, and so here I'm just telling you the answer. Hey, 2x plus 14 can be factored, okay? Or can the factor form of 2x plus 14 is 2 times with a sum x plus 7. But now we want to learn a solid method of how we can go from here into a 2x 2 times in parentheses x plus 7, because we don't always easily recognize. Easily recognize. So that's why here we want to learn some solid technique right here. Okay. All right. So factoring a polynomial expression into a factor form right here, into a factor product right here, is sort of like the reverse process of the distributive law. All right. And so the work I've been showing on the other board earlier is just really similar to, think about back in the days right here when you were in middle school or even elementary school and you're learning lower level math, like that beginning level math. I should have said that. So your teacher has been saying, hey, when you have 3 times multiply with a sum 7 plus 2. Okay, on one hand, more naturally with order of operations, you can go, since 7 plus 2 is included in parentheses, order of operations says you must first add the 2 here, so 7 plus 2 is a 9, so we have 3 times 9 consequently, and that equals 27. That's one way of handling it. But then on the other hand, your teacher back at elementary school or middle school must have taught you this. Hey, 3 times in parentheses 7 plus 2 can also be done as 3 times 7 as a product plus 3 times 2 as another product. Okay, that now looks familiar, doesn't that? And so 3 times 7 as, now order operation comes in right here. 3 times 7 as one product, that's 21. 3 times 2 as one product, we have to do all of the multiplications before addition. So 3 times 2 is a 6. 21 plus 6, that comes out 27. And that's how the teachers your teachers long ago should have said, hey, see, 3 times, in the end we made a conclusion, 3 times of the 7 plus 2. Okay, one way to get the answer is through the direct computation, but another way of doing that you can do as 2 separate products, 3 times 7 plus 3 times 2. Okay, that's a little bit of a bring back some memory thing. Okay, but it all exists and it goes into our formal algebra course here. All right, and so now let's formally learn that technique. How we can bring a polynomial expression into the factor product, into a factor form. That's what it means by factoring a polynomial expression. But the essential tool that we use is to find the GCF. Okay, so let's get to it. Allow me this time to approach the demonstration through an actual example, and then along the way you will learn the technique and it will solidify your understanding. So continuing from the earlier example, let's look now at example 4. Okay. The worded instruction says, let's bring this, factor 24m plus 30. Factor that expression. Factor this polynomial expression. We got 2 terms. See, addition signs right here says that they're separate out that we got 2 terms. Each term here has only the multiplications or the powers or lone numbers. All right, so now upon recognizing that these are 2 separate terms and the technique we're about to do here is finding the GCF, here's what I'm doing. I am going to find the prime factors in each of our terms here. So 24m can be written as a product of 2 cubed times 3 times m. Okay. And then 30, the other term in our algebraic expression, I can see that as 2 times 3 times 5. After writing down all the prime factors of our product right here, of our number. And so in that way, the GCF, according to our previous learning that we have gone through, then the common factor I recognize here is a 2 and least power is a power 1. So I just 2 to the first power. Another common factor is a 3. So times 3. And then the 5 and the m, those are just non-common. And so now GCF here comes out being 6. After we have found the GCF, now GCF is just part of the work to a bigger problem right here. So that means 24m plus 30 can be re-expressed as. So 24m, the term here is 2 cubed times 3 times m right here. So I'm going to rewrite this here as a factor 6, but times. So 6 here came out from 2 times 3. So 2 times 3, after isolating it out right here, then we have a 2 squared that remains. A 2 squared that remains times m. So 2 squared is a 4. So 4m here. Okay. So 24m is written as a 6 times 4m. Another way of seeing this, now this is just one way, if my way of explaining it's not convincing, there's another way of, you can see this. Just think about 24m initially as the beginning term right here. And let's divide away. Okay, and you're going to divide away by 6, the common factor. And we can simply cancel out, and then making that 4m. That's another way of seeing it. And so, and now I'm going to rewrite it as 24m as 6 times 4m. And so in that way, there are different ways to interpret that. But after we have found the GCF, now 30, the plus sign is still here, but 30 here can be seen as 5 times 6. Or it's better to write as 6 times 5. Once again, if you don't see that so quickly right there by recognizing the products, I recommend thinking of that as just 30 divided by 6 on scratch work. 30 divided by 6 give me 5. So that means 30 is 6 times 5. Okay? And so now 6 times 4m. Should have also put that in parentheses. 6 times 4m and 6 times 5. 6 times a 4m and 6 times 5. And so now I see, let me underline right here. 6 here is the greatest common factor. Common factor. 6 is the greatest common factor. Common factor. So common factor multiplied with 4m. The same factor multiplied with 5. And it's added. So distributive property allows us to, once again, things that we've learned back in some courses long ago. We bring out the 6, we keep a 6 out. Okay. Now in a parentheses, you can do the following. Just simply 4m plus 5. Yeah. All right, so ladies and gentlemen, this is our final factor product right there. All right, 6 in product with the sum 4m plus 5. And that's how we factor out, or another way of saying 24m plus 30 can be written as 6 in parentheses 4m plus 5. That's how we have done factoring. I have turned this polynomial expression into a factor product right there. All right. And so now with the example we have just done, where you have seen the technique right there and was introduced through the example, think about what if the problem was originally, so allow me to bring in a what if right here. The problem I wrote down was a 24m plus 30, but what if it was a 24m minus 30? Okay, this is still a polynomial expression. 2 terms, because remember, when you're looking at an algebraic expression, the addition sign or a subtraction sign separates the terms right here. And so you got 2 terms, 24m and 30. And then that subtraction sign is just an operation existing between the 2 terms. So you're still doing the same thing right here. 24m can be written as 2 cubed times 3 times m. And then 30, another term here, being expressed as a product of 2 times 3 times 5, like that. So these are the prime factors. So exactly the same like how I've done in example 1. And the only thing different is the sign right here. It's being subtraction. And so when you're actually getting into doing it, okay, so now 24m minus 30. And by the way, right from here, the GCF comes out, of course, the same way right here. 2 times 3, common factor, 2, least power. Put it here, common factor 3, another 1, least power is 1. That's why GCF is 6. And so I can again see that 24m can be expressed as 6 times 4m. And the exact same explanation that can be done again. And then the 30, the other term, can be expressed as 6 times 5. The only difference, so everything really stays exactly the same, except for that sign. The original problem could have been minus, like that. And so we put the minus sign here. We put the minus sign there. And so now distributive property also holds on subtraction. So here we got a common factor. Yes, it was a GCF, but it's also the common factor ultimately. So now you can put it as 6 in parentheses, 6 multiplied with the entire 4m minus 5. All right, and that's how a problem like that can be done. All right, so I brought in a what if situation like this, but it's an additional problem for everyone to see through of how you can do it. All right. All right, and so now let's look at another problem right here. I call that example 5. I want to factor. All right, I want to factor 6x squared y cubed minus 15x cubed y. This is a polynomial expression, and let's factor it out by finding the GCF. And so once again, now in this example, in this problem, the polynomial expression we have here, right here in this problem, 2 terms because of that subtraction sign right here. So everything around it, it separates the terms around it. Okay, so 2 terms. So right after calculating down the 2 terms right here, I'm going to go ahead and find the GCF. So 6x squared y cubed. All right, writing the prime factors for 6x squared y cubed. I see 6 here as a product of the primes 2 and 3. And then multiply with x squared and multiply with y cubed. That's how I write the prime factors for 6x squared y cubed. We've learned a little bit from at the end of example 4 earlier about what to do with the subtraction. So the subtraction or addition just to simply serves the purpose to separate out the terms. So in the end, I just need to simply focus on the other terms. So 15x cubed y. Let's find the prime factors for 15x cubed y. So here I'm looking at 3 times 5 times x cubed times y. All right, and so now I'm ready to find a GCF. So GCF here, 3 is a common factor. The least power is 1, so let's put it down, 3 to the first power. 5 is not a common factor. X is a common factor, is a common prime factor. The least power is 2, so it's going to be x squared. Put in. Y is another common prime factor. Least power is y, is to the first power, so we put in y to the first power. So now that means the final GCF between our 2 terms, the final GCF comes out being 3x squared y. All right, 3x squared y. All right, so things starting to get a little more challenging here. So, all right, so now back to the problem right here. 6x squared y cubed minus 15x cubed y. Right. First term, I can write it as 3x squared y. That's our GCF. Multiply with 2y squared. Right? That's how I have re-expressed my first term as a product between the GCF that we found previously and the product of the remaining factors from our beginning term. Okay, so how in case you're not following along of how I can get that so quickly, again, I brought in this technique right here. Think about the whole 6x squared y cubed divided by 3x squared, the GCF that we have found previously. And so 6 cancel with 3 gives me a 2. Okay, and then x squared cancel with x squared. So there's no x left. Y cubed cancel by y gives me a y squared. That's how I ended up with that remaining product. Okay, and now for the other term, minus. So I'm going to rewrite our GCF right here, 3x squared y, but in product with 5x. All right. So how do I know 5x so quickly? Again, 15x cubed y. That's our original term right here. Just simply divide that by the GCF that we have found previously. 3x squared y. 15 cancel with 3 gives me 5. X cubed cancel with x squared gives me x. Okay, and the y cancel with the y. There's no y left, and that's how I ended up with the 5x. All right. And so now upon re-expressing each of our terms as the products between the GCF and some remaining factor, GCF and some remaining factor. Okay, remaining factor right here after the GCF. So now with distributive law, the distributive property, we can isolate out the 3x squared y as one factor. And we multiply that with now as a sum or as a difference. See, 2y squared is the first term. After isolating out the GCF, 2y squared left over, 5x left over. The operation existing between the two terms is subtraction. Now we put subtraction signs there. All right, so that's how we have factored our beginning out polynomial expression, 6x squared y cubed minus 15x cubed y. And that is factored into this. So the work here is part of the work, but formally as a steps here, see, we rewrite our problem here, our beginning polynomial expression as how we express that as GCF times some remaining factor, GCF times some remaining factor, and we pull out that GCF in front and produce parentheses. All right. And so at this end point of two examples that demonstrate how we can do factoring right here, then now I've been staying with polynomial expressions with two terms, but can this process right here be done with three terms or even more? So basically, yes, we can factor a polynomial expression with more than two terms. Okay, but of course those are just additional problems, additional experience I would like to add into your learning. So I will not put that all in this same video lesson here, but I will produce a separate video lessons to cover those problems where we learn how to factor a polynomial expression with more than two terms. Okay. All right, let's now bring in another example where we can factor by finding the GCF here, and I call it example 6. All right, so here we want to put this polynomial expression into factor form right here. So the challenge that's waiting for us here, well, this is one term, and this is another term, and we got additions going along with that. All right, but here's the challenge that's waiting for us. Now, the first term here has a negative coefficient. So in a more commonly way of saying that we have a negative. The first term here is called the leading term. So we have a negative leading. See, the leading term has a coefficient being a negative. So we refer to that as the case we have here specifically is a negative leading coefficient. Okay. So let's see how we can factor by finding the GCF when we are handling a problem with negative leading coefficient. Okay, and so this addition sign right here once again separate the two terms. But the first term now, let's include a negative sign, so we got minus 6a squared. We didn't see this back in our lesson specifically learning about GCF, but we can just treat this as a little add-on experience right here. So minus 6a squared. All right, let's think of that as minus 1. Because that's the negative 6 right here can always be thought of as a negative 1 times 2 times 3. So we put the prime factors on all of that, and we put a negative 1. Okay, that explains for the negative 6. So negative 6 comes out as negative 1 times 2 times 3. Okay, and then just like that, the variables we put it there with the powers correspondingly, and then the other term was a 36a. But since the leading coefficient was negative, so now we recognize a negative sign in our one of the terms here. And so let's also see this as negative. Like I said, we purposely see this, even though positive 36a, but let's see that as negative 1. Okay? And then times another negative 1 times 2 square times 3 square. It was positive, but the positive here I'm seeing that as a negative 1 times negative 1, and then times 2 square times 3 square, and then times a. All right, so that's how we do the prime factors. And so that's what you need to realize is we only doing this, splitting that into the negative and the negative here because the leading coefficient was a negative. So I purposely want to see that negative as well in the other factor, even though it was not negative even though it was not originally negative. Okay, so positive 36, I'm seeing that as negative 1 times negative 1 times 2 squared times 3 squared, okay, times a. All right, and so now here's how I'm seeing my, and so the GCF here. All right. See, and really the negative 1 here is just the negative 1 squared as a prime factor is negative 1 all squared, so the least power is a negative 1. See, common factor, but least power is negative 1. So I put the negative 1 here times the 2 and is another common prime factor. Least power is a 1, so I put the 2 here. Okay, the 3 is another common factor, prime factor, but least power is a 1, so I put the 3 there. Okay, and then a squared and a common factor is an a. Least power is a 1, so I put an a here. So our GCF comes out being minus, see, negative 1 times 2 times 3 minus 6a. That's how I'm seeing it, minus 6a. All right. And so now, after breaking it down into the, and find the GCF here, here's how we can see the work on our problem. So, back on my board. Now, I need a lot more space now this time. So, minus 6a squared plus 36a. I am going to see this as the GCF was minus 6a, so minus 6a, and the other factor that remains is now just simply a. And once again, how do I know this so quickly? Think about it. Think about that as minus 6a squared divided by minus 6a. So the minus 6 got canceled away, and the a squared canceled by a, get me just a. And that's how we have that. Now the other term plus, now I'm seeing this as minus 6a as a common factor. Okay, the GCF multiply with the other one being minus 6. So how do I see the other factor so quickly? 36a divided by minus 6a, the common factor. 36 divided by negative 6 give me negative 6. And then a cancel with a completely. Okay, and that's how I got negative 6 there. And so now, here's how I'm seeing it. I'm going to factor out minus 6a as our GCF. The remaining terms are going to be a plus minus 6. All right. And in a more intellectual way right here, we should have used brackets for another level of parentheses. But so these are the two remaining terms, a plus minus 6. And of course, take your step, take it slow, and then eventually when you get fluent enough, it's going to go faster. But so now minus 6a in parentheses. Now, we've learned we're beyond that point. Plus or minus, you can all rewrite it as a minus 6. That is our final common factor. Okay? And the approach I'm doing here may not be the best one, but at least I see it. It's most solid and it shows all of the reasonings behind the scenes like that. Okay? But once you're fluent enough, you don't have to, exactly follow step by step. All right? But so now minus 6a squared plus 36 will equal, in factor form here, minus 6a in parentheses a minus 6. All right. All right. So after we have learned, throughout the three examples, example 4, 5, and 6, and how we can factor a polynomial expression by finding the GCF, let's bring in some skill that's quite vital to our work as well. We checked our final answer. We're going to learn to check the final answer. So let's say back in example 4. Okay. We were asked to factor 24m plus 30 was factored into 6 times, in parentheses, 4m plus 5. So yes, we don't want to repeat the steps over and over just to check the answer, but there's always a vital, quick solution to the solution to check whether you have landed into the correct factoring form. Remember, the essential theme we've been using here is the distributive law in this. And so to check whether this answer is the correct answer, the correct factor form for 24m plus 30, all you do is simply multiply 6 with 4m, multiply 6 with 5 here. So 6 times 4m plus 6 times 5. Are we getting, and so 6 times 4m gives me 24m. 6 times 5 is 30. So are we getting that expression that's exactly matching? That is exactly matching with the beginning polynomial expression. And yes, that is a check right here. And so that's how we know that we have found the correct answer for example 4. That our factoring work in that problem of example 4. So the same way in example 5, we were factoring 6x squared y cubed minus 15x cubed y. And the factor product came out being 3x squared y in parentheses, okay, 2 in parentheses 2y squared minus 5x. So how do we know if we have arrived at the correct answer? Once again, the GCF is here. Just simply multiply that to each term in our parentheses. So 3x squared y times 2y. 3x squared y times 2y squared minus 3x squared y as a 1 GCF times with the 5x distributive law. And that comes out, see, multiplying all that together, we have 3 times 2 is 6, x squared times y cubed, minus 3 times 5 is a 15, x squared times x is x cubed times y. And this is an expression that exactly looks the same with the beginning polynomial expression. And in the very last problem that we've done in example 6 right there, our answer came out being minus 6a in parentheses a minus 6. So how do we know if we found the correct answer? So once again, from the GCF that we have found, let's just multiply that back to each term. And I've been drawing arrows to indicate we multiply according to the distributive law. Multiply that to the first term, multiply that to the second term, and watch out for sign change in this specific case right here. So minus 6a times a gives me, well, let's write it down, minus 6a times a. Minus, and then we got minus 6a times 6. Minus 6a times a is a minus 6a squared. A times a is a squared. Minus 6a times 6, but times with negative sign right here makes it positive. So now 6 times 6, 36a right there. And so we have landed into an expression that looks exactly the same as our beginning polynomial expression. And so this method right here, this technique right here introduces us how we should be able to check our answer. All right. All right, and so now at this point, of course, I could not reach all details here, but I have covered enough understanding in terms of how we can factor a polynomial expression by finding the GCF. And so at this point, and it's a skill that will live for the rest of your mathematical career. So right now, admittedly, it is quite early to see all of the reasons why we're learning how to do factoring. Okay, but at least the closest impact I can introduce here at our level, because anyone viewing this level, viewing this video lesson is quite early in your mathematical learning. And so it's not too practical to keep looking for why and why, because you haven't seen enough applications. Okay, but at this point, let me bring in a couple of things that you have seen, and now with your understanding about factoring will help you clarify your understanding from all those years right there. So let's look at some impacts. Well, what's good about being able to do factoring polynomial expression, and specifically using by finding the GCF right here. So let's think about something like this. A couple impacts right here. Let's say we have a rectangle, and rectangle is famously known for some length and width, and these are the same and the widths are the same. Okay, so that's a rectangle. So the formula for calculating, as I'm saying this, everybody knows, the formula for calculating the parameter for a rectangle like this is, see, it's been always twice the length plus twice the width, because these are exactly equal, so length times plus length, right? 2L plus 2W. And so now think about it. An easier way of doing this. Some textbook has been doing this. 2 times just length plus width. Another way of doing that. An easier way of doing that. Instead of 2 multiplied with L and then add with 2 multiplied with too many operations involved here. Whereas here we only need to add 1 time the length and the width, and then both of those multiply with a common factor 2. Do you see the impact here? The impact here is that by what we have done here, the expression I'm writing here, this form right here is the factor form of 2L plus 2W. I have just now factored out the 2, the common factor that we seeing so clearly in here. And then factoring it out, it saves us, in a problem like this, calculating parameter of a rectangle, it saves us some operation. So we only need to add 1 time, and then after that additions we multiply by 2. Okay, so a quick formula, the formula to calculate the parameter of a rectangle that we used to know can be quickly done by just length plus width, right? 1 time and then multiply with 2. Okay, that's one direct application that everybody knows. Another one. So just think about something like this. Let's say if you have a 3x plus a 5x, okay, 3x plus a 5x. Now at this point in our experience, after learning about factoring a polynomial expression by finding a GCF here, then the GCF is x, GCF is x. Okay, then we can do the following: 3 plus 5 times x in factor form. And 3 plus 5 can indeed be added further because these are all just numerical values. So it gives me 8x. Okay, so that's just straight out theoretically from the factoring methods. But here's the impact, the real impact I want you to understand. It has been long that, you've seen expression like this: 4x squared plus a 3x plus a 5x plus 1. So sometimes you have a lengthy expression like this. And your instructor, including me, has always been referring to these as like terms. Like terms. So we've been using the term, we combine like terms. So 3x plus 5x is combined as 8x. So the expression here becomes, 4x squared plus 8x plus 1. But see, what's the operation, what's the truth behind the scene that allows us to combine like terms? The concept here was we were factoring out the GCF being the like variable, the GCF being the variable, and then we add those coefficients together. And so before you were learning formally about the factoring finding the GCF, then we refer that to make it easier, combining like terms. But the truth behind combining like terms is that we were doing factoring work. All right, and now we hit to our last methods being introduced in this particular video lesson right here. Let's learn how to factor of course, a polynomial expression, but by grouping. All right, and allow me now to introduce the methods through particular examples again. And everything you have learned from the earlier part of the video lessons will be essential the methods being used in here. Okay, so let me bring in now example 7. Let's factor the following: xy plus 3y plus 2x. All right, so we have a polynomial expression here, and more than one variable is involved, and you've seen all of this. But so now, factoring by grouping, this is the way how I see this. This is a little more advanced, enhanced level of factoring by finding the GCF. Okay, so here's how I show you the work right here. Now let's just for now stay with its natural arrangement. I'm using that word, the natural arrangements, the natural order of these terms here. So there's the xy term comes first, and then there's a plus, and then there's a 3y terms, and then plus, there's a 2x terms, and then plus 6. So we got 4 terms in this particular polynomial. Okay, and what I said earlier, let's stay with its natural, the way how it's given right here. That's what I call the natural arrangements. Okay, and so then in that way, here's how it's called by grouping. So here's how I'm doing it. I'm gonna group. So xy and 3y right here. I'm gonna group them as one group. So positive xy and positive 3, because of that sign. So positive 3y, I'm grouping them as one group. Okay, and I'm grouping 2x plus 6 as one group. Okay, and it's addition right now. It's adding. All right, and so now I have produced two separate groups. All right. So now with a little bit of algebra, with the skill we've learned prior to this lesson, prior to this point here. Now I'm seeing xy plus 3y as one small polynomial expression. And so I can apply the skill we have learned throughout example the 4, 5, and 6 right here. Let's factor out the GCF in these terms. So a group here is one little polynomial expression. Let's recognize the GCF here. The GCF for these two terms is the y. So I'm factoring that out. And so I'm skipping the process a little bit because the process for factoring out the GCF was shown, so you can do that on scratch work. For example, you can think of xy as x times y. 3y as another term has 3 times y. So common factor is a y. So xy plus 3 times y, you can see this as, and then of course here the GCF is y. Okay, and so you can see this as xy is x times y, quite trivial, plus 3 times y. So the common factor right there, it's y times, and then x plus 3, the two remaining terms. Okay, and so I just, in case you really want to look for that, how we can apply the previous learning into this current problem right here. That's how we're doing it, recognizing the GCF and all that. But so ultimately, so xy plus 3y can be factored as y, the GCF, times x plus 3. You have seen that in my scratch work. And now I'm putting the plus sign here. And it's pretty vital that right now it's plus sign, and I'm using the plus sign here. But the plus sign is not the only cause for all of these plus signs. When we have to some other additional problems, I will explain better. But for now, these two terms are here. Once again, we can easily recognize that there's a common factor of 2. So the GCF being 2, I pulled it out. X plus 3 is what remains. So the quick scratch word for this to explain, and you can skip this. See, we had 2x plus 6. 2 terms, 2 times x. And then 6 here in prime factors. So 2x is 2 times x. 6 here in prime factors give me 2 times 3. The only common factor is there. Okay, so GCF comes out being 2. And so 2x plus 6, according to what we've learned in the previous topic, then we're looking at 2, the GCF times x, plus 2, the GCF times 3. That's how I rewrite the 6 right here. And so now we isolate out that GCF, it's 2, and then we have x plus 3. Okay, and so in this work we have 2 times x plus 3. But now, if we're looking at this a little further, a little closer, a little more closely, I'm seeing that, and you have seen this in some of the earlier problems. If I see 2 terms, there's one term, and there's another term. And then I'm going to double underline this. That is a GCF. We have had some examples back in the lessons where we were learning about how to find GCF right here. We have seen we can take a GCF being as large as a sum like that, an expression being a GCF. And so now I recognize, hey, there's a GCF being the x plus 3. All right, so now I'm gonna isolate out the x plus 3 as my GCF. So after isolating out the x plus 3, my GCF, that's just y and that's 2. That's y and that's 2. The sign that connecting them, addition. The operation that connects the two terms right here, that's addition. So I have completely factored. My beginning polynomial is now factored into x plus 3 times x plus 2. And the technique that we were doing here was by grouping. See, the first two terms, and let's just for easy case, and of course in some other, I will have additional the video lessons to show you how you can creatively rearrange the terms and sometimes to make it work. But the most default situation is just to stay with its natural order, with its natural arrangement like that. So whatever the order of the terms right there, let's leave it like that, and we're gonna start grouping out the terms like that. All right. All right. So here we're at example 8, another problem, how we can factor a polynomial by grouping. Okay. So let's take the experience we've had from the earlier problem, example 7, into this. Let's stay with its default, with its natural arrangement for now. Okay. So with its natural arrangement, I mean, however it's currently ordered. So x squared comes first, and then minus 3x, and then minus 2x, and plus 6. Okay. So here's how I'm doing grouping. I'm going to just group the first two terms, positive x squared and the minus 3x, positive x squared and the minus 3x. I'm going to group them together. Okay. Now I'm going to group the next two terms with minus 2x and plus 6, minus 2x and plus 6. I'm going to group the next two terms. But now the scary part is what's going to be the operation that connects between the two groups here. The default one, in case you have already included the negative signs, and this is the scenario that's making it different with the earlier example that I want everyone to learn through this right here. That in case you have already included the negative signs, right, in your grouping, then the default one, the default operation that can be used always applies. Okay, and so now you have minus 2x plus 6, the way how it is, all the signs included, grouped together. Okay, and then so the operation that connects the two groups, plus sign. That's one thing I want you to nail it down like that. So now the first group, now I can see that as a one little polynomial expression. So at this point, allow me to assume you have reached a certain level of fluency. So in that case here, let's say x squared minus 3x. GCF is going to be x. So I am going to write the x separate out, isolated out. So now inside of my parentheses is here, I have x minus 3. So think about x squared divided by the GCF that we have, x remains. 3x divided by the GCF x, we got the 3 remains. Subtraction signs remain the same. Okay. Plus, yes, plus. The GCF for this group right here, the way how I see it now, this group is another little polynomial expression. The way how I'm seeing it, 2 terms, right? And negative leading coefficient. We have learned how to handle this situation, this scenario back in our earlier learning. And so now I'm gonna consider the minus 2 as our GCF. So now minus 2x divided by minus 2 gives me an x. 6, positive 6 divided by negative 2 gives me a negative 3. All right. And so now at this point, I can see the following. I can have, see, these are 2 groups right here, but they now think of these as 2 separate terms because there's the addition sign that separates them. But I have a common factor right here. I have a common factor that I underline right there, x minus 3. So further, I'm going to factor out the x minus 3. Okay, because that's a common factor. And then, according to the distributive law, we have remains x plus with that minus 2. And that's the reason why I've been writing the plus sign the whole time. And so now plus a negative 2 really comes out finally as, so I have x minus 3, the other factor. And then now it's x, well, plus and a negative 2 is the same as x minus 2. All right. And so this is the factor form that I have done, that I have put this beginning polynomial into that final product right there. All right.